All right, this is our first lecture in our new chapter, chapter 5. Newton's Laws of Motion is the title of the chapter. In, let's see, AP Physics, we call this dynamics. We've been studying kinematics. That's actually projectile motion and uniformly accelerated equations that you guys have learned. And now we're moving into dynamics. So what causes an object to move? What causes an object to accelerate more appropriately? So my goal today is to teach two things, is the first law and the second law. There are three laws, Newton's first and second and third law. So we're going to talk about the first and the second. But before I do, this is not from your book because I don't think it does a very good job. We need to talk about forces because this chapter will have a lot to do with forces. We're going to talk about forces quite a bit from now on. So what is a force? Force is commonly thought as a push or a pull. So if you were to push, let's say, a box across the floor, you're actually putting a force on the box. Or let's say, for example, you were to pull a wagon, that's a force. So we can push or pull stuff, objects, with a force. And there's different types of ways that that occurs. So a force is a vector, so therefore it has both a magnitude and direction. And so I can push or pull an object in a horizontal direction. I can push and pull an object in the vertical direction. I can also push and pull an object at an angle. And so I can then break that into components. So now I know the force can be, because it's a vector, it can have both a component in the X and Y direction. So I want to talk a little bit about what types of forces there are first. So the first one I want to talk about is a contact force. So when we pull, for example, on a spring or pull a wagon or kick a ball, those are all examples of a contact force, okay? So for example, a book sits on a table. There's actually a force that the table puts upward on the book. It's in contact with it. But there's also a force of gravity that is pulling down on that book, and that would be considered a field force. Field forces do not have to touch the object, but they're in some sort of field. And the one that we'll talk about the most is the gravitational attraction between two objects. That's the force of gravity. So once again, if the book is sitting on the table, okay, the table is actually pushing upward on the book, because it has to counteract the fact that there is a force of gravity pulling down on the book. So there are more than just gravitational types of field forces. There's also electric force between two charged particles. So you guys have heard about opposites attract. And let's see, if I have two particles, one's positive and one's negative, they actually have a force between them that is an electric force. That in that case, it's an attractive force, but they're not touching one another, and that is why it's considered a field force. Now, if they were both positive particles, they want to repel one another. So the electrical force was going to push them away. So those are examples of a field force. So gravitational, electrical field force. There's also nuclear forces that we have, and we can have them in radioactive decay. We have also magnetic force. Okay, so these are all types of field forces. The one that we are going to work with in this class is gravitational attraction. So we have now discussed what a force is, which is a push or a pull, and we know that we have different types of forces, some that are in contact with one another and some that are field forces. Gravitational force is, let's see, which one? There's different types of forces, like I said, and in the field forces, there's an order of strength. The strongest is the nuclear force between subatomic particles, then the electromagnetic force, and then the weakest is gravitational force. Okay. All right. Now we're into first law. So now we know that there's these forces that exist in all around us, and they can be in contact force or a field force. Okay. Newton's first law. So originally, scientists believed that the natural state of matter was to be at rest. So everything that existed, objects, particles, wanted to be at a state of rest. So if I have a car that's traveling down a road and coasting, that it's trying to do everything it can to get to rest. Or if I have a book that's happy because it's at rest. But Galileo began to think that objects actually prefer to continue in their original state, which could be at rest or motion. So, for example, think about a hockey puck. We'll talk about a hockey puck quite a bit. That's sitting on ice, that we have a velocity. And if that ice and hockey puck between them, there is perfectly no friction, then in theory, that puck would travel forever. And this actually is the case. We definitely uh, know for fact that basically objects want to stay in their original state of motion. So that could be at rest or at with some velocity. They're happy to be traveling down the ice with no friction forever. Think of space travel, for example. If I were to throw a ball in space, it would just travel on forever because of Newton's first law. So he formalized this idea as Newton's first law. Basically, when a net force is applied, the velocity changes. So if I have a book that's on the table that's at rest, it's happy until I come along and um, create a force on it. So if I push the book, I have enough force that I overcome the frictional force and it will start to accelerate across the table. Now, if I let go of the book will slow down because, again, the frictional force is slowing it down. If I were to repeat that process on a smooth wax surface and completely eliminate the frictional force that's there, then in theory, once I have that book in motion, the book will continue in motion forever. Okay. I know that's hard to imagine because it's very difficult to remove all frictional forces on a table surface. But if I was capable of doing that, I would be able to create a book that would travel across the surface forever and it would not slow down. So Newton's first law states an object at rest remains at rest as long as no net force acts on it. So it will stay at rest if there's no net force. Okay. And we'll talk about what that net force means in just a minute. An object that is moving with a constant velocity will continue to move with that velocity forever and ever and ever in the same direction as long as there is no net force. So, um, Newton's first law tells you what will happen when the net force net, is equal to zero. That means that whatever the state of motion that the object is in, it will continue forever and ever, whether it's at rest or whether it has some velocity. So here's some examples. Now, we need to talk about this word net force. What does the word net mean? It means the sum, the total. Okay, so the total force must be equal to zero. I'm going to go back to my book that's sitting on a table. I told you that there's a force of the table pushing up on the book, and there's also a force of gravity pulling down on the book. Now, this is in the positive direction, this is in the negative direction, and the total force, okay, in the y direction, or the net force in the y direction is equal to zero. And that is why that book will remain at rest forever until someone then imposes a unequaled force on the book. So the object will stay at rest as long as there's a no net force. So you can think of a couch potato. This potato has a force pushing upwards on it, and it has a force of gravity pulling downward on it. And if I had a bus that was traveling along the road and there was no net force on it, it would continue at the same speed with no acceleration. The acceleration would be equal to zero, not equal to zero, if the forces on them added up to zero. So the net force is the total force. In this case that I showed you over here, I had two forces. I had force of normal, force gravity. They equal each other and they cancel each other out. So first law makes space travel possible. After a few minutes of a powerful thrust, a spaceship can coast for months or years. Its velocity is only slowly changing with time under the relatively faint influence of distant suns or planets. Okay, so if I were to fire my engine on a spaceship that's way out there in space, it will continue at that direction forever and ever. If it wasn't possible, we'd run out of gas. Okay, all right, so that's first law. It tells you what happens when the net force is equal to zero. I will have no change in my state of motion. Now, that's what first law tells me. Now, what is second law tells me? It answers the question of what happens if I do have a net force. So what if I have something that is not equal to zero? Well, here's what Newton's second law says. I'm going to experience acceleration, okay? I'm going to have, the object is not going to remain in its current state of motion. It's going to change. So for example, if I have my book and I come along and put a force, so I'll call it force applied, and I have enough force applied, I'm going to accelerate, and I'm going to accelerate to the right. And so it started at zero velocity, and then the velocity starts to change. And by definition, you know that acceleration is equal to the change in velocity over time. So there is an acceleration that occurs because of that force that was applied to the book. Okay, continuing on. So here is what your equations look like in your book. And they break it down. I don't like it, but they do. They break it down into two different scenarios. If I have a single force acting on it, which I have shown up here, but what if I have a whole bunch of forces acting on it? Sure, I could have another force on there. I could have a force I could pull and push at the same time. Maybe this is 1 and this is 2. Maybe there's a force that's trying to slow me down. How about friction? That would be my third force. And so I would have to add up all of the forces to determine what my net force is. And that is right here, your net force. So remember, I could have more than one force. And if I want to know what's going to happen to the motion of the object, whether or not it accelerates or not, I have to look at all the forces that are acting on the object. Okay. All right. So let's rewrite Newton's second law. We know that the force is equal to mass times acceleration. How about the sum of the forces? What does that mean? This means sum. How about that equals the total? How about that equals net? So I have the sum of all the forces, which is equal to the net force, is equal to mass times acceleration. So the net force is equal to mass times acceleration. This is Newton's second law. Okay, so let's talk about what happens if I have a force. So let's look at this problem right here. I have a force, F. I don't know what it is. Let's call it some number F. And I have a block that has a mass M. And we'll say that if I apply that force to mass M, I will achieve an acceleration of 2 meters per second. What happens if I then change the force to 2F? Well, if the mass stayed the same, which it did, and force is equal to mass times acceleration, and I doubled the force, what happens to acceleration? Well, it has to double. So we call that directly proportional to the net force. So as the net force increases by a factor of 2, the acceleration has to increase by a factor of 2. They are directly proportional. What happens if I then keep the same original force, but double the mass? Now I have 2 blocks that have a mass M. Well, because force is equal to mass times acceleration, and I just doubled this mass, I kept my force constant, then acceleration has to decrease by that same exact factor. And it was decreased by a factor of 2. I doubled the mass, so I had to take the acceleration and decrease it by a half. And this is what we call inversely proportional to the mass. So acceleration, okay, is directly proportional to the force. and inversely proportional to the mass. Okay, we haven't talked about units of force. Units are super important, as you know. So let's talk about that. Force is equal to mass times acceleration. Well, what is my units of mass? It's in kilograms. What is my units of acceleration? Meters per second squared. So I have a force is equal to a kilogram meter per second squared. However, we have given this a new name. It is called a Newton. So a Newton is a unit of force, and inside of a Newton, it is a kilogram meter per second squared. So this kilogram meter per second squared is equal to a Newton, and a Newton is symbol will be a capital N. So all forces have a unit of Newton. So let's take a look at this. We are using the SI system in class. So we have mass, we use kilogram, acceleration, we use meters per second squared, and Newton is equal to a kilogram meter per second squared. Now notice our US, we use feet per second squared. And I'm sure this is some surprise to you, but pound is not a measure of mass. Pound is actually a measure of force. When you step on a scale in the bathroom, you're actually determining the amount of force that you are putting on the scale. And that is related to your mass. And in units of, in US, the mass is actually measured in slugs. Probably a little fun fact that you never do. Mass in the US is considered a slug. We never talk about that, but nevertheless, pound is not a measure of your mass. It is a measure of the force that you are exerting on the floor, for example. All right, let's do a quick problem. We have an 1,800 kilogram car that has an acceleration of 3.8 meters per second. So we have a car. We know the mass is equal to 1,800 kilogram. And I know acceleration is 3.8 meters per second squared. What is the force? So we're asking for force that is acting on the car. So we know that the sum of all the forces is equal to mass times acceleration. How many forces are we asking about? We're asking about one, or the net force. And so I know F is equal to ma. And I was told the mass, which was 1,800 kilograms, and the acceleration is 3.8 meters per second squared. I would multiply 1,800 times 3.8, and I get 6840, and that is in kilograms meters per second squared. How about 6840 newtons? That is your answer. All right, so that concludes my lecture for today, and I have some problems that I would like for you to try on your own.